Hello, multivariable calculus students. This is Mr. Johnson, and this is the second video for section 11.6. We're going to just kind of review. I already mentioned what the maximum value of the directional derivative was when I introduced the idea of that gradient. So I'm just here's the formal theorem. We're on page 37 right now, and I wanted just to reiterate it really quickly, and then we're going to move on. But remember that we're dealing with the gradient vector and the unit vector, which is going to be our desired direction. And in general, what we're dealing with is a situation where we're calculating the directional derivative by the dot product. So we have the directional derivative in the direction of u of a function f equal to the gradient vector dotted with the unit vector. And we developed that by the projection of the gradient onto the unit vector. So we already talked about all that stuff. And then I did mention as well, and so this is still review, that the other formula for the dot product is this one with the magnitude of the gradient multiplied by the magnitude of the unit vector multiplied by the cosine of the angle. And so when you think about the maximum, and this is what the theorem says, but the maximum of your directional derivative is going to be the value such that cosine of theta is equal to 1. And of course, that's going to be an angle of 0. And so when you think about what that means with regard to how these angles interact, if this angle is 0, then the gradient and the unit vector are pointing in exactly the same direction. So when does the maximum occur? Well, the maximum occurs in the direction of the gradient. So the gradient and the unit vector are in the same direction, and the actual maximum value, so the maximum rate of change of a function at a point, is going to be the magnitude of the gradient. So that's what this theorem says. I just wanted to reiterate it again. I know we talked about it already in the first part of the unit. Okay, let's do some problems here. We're looking at example 6, and we have the function x e to the y, and we want to find the rate of change of the function at the point 2, 0 in the direction from P to Q. So notice the graph. This graph is not terribly helpful, but that's the surface. This graph is going to be the level curves, and we're dealing with this point right here at 2, 0. The gradient, if you remember from the first video, the gradient by definition is going to be perpendicular to the level curve. So the gradient will be pointing in this direction because that is perpendicular to this particular level curve. However, we're looking for the rate of change not in that direction, which would be the max rate of change. We're looking for the rate of change in the direction to Q. So our first step is to create a vector v that is from P to Q, and that vector is going to be -3/2. Just remember you're subtracting the components there. This is dating back to chapter 9 and how we looked at a vector between 2 points. We also need the magnitude of that because we need to be able to turn this into a unit vector. So the magnitude is going to be -3/2 squared plus 2 squared, which is, let's see, that's going to be 9/4 plus 4, which is 16/4. So we get the square root of 25/4, which is 5/2. All right, so our unit vector that we're searching for is going to be 2/5, because we're dividing by that, of the vector -3/2 and 2. Okay, and then our next step is that we want to calculate the gradient. So the gradient vector of f will be e to the y and x e to the y. And again, we're going to evaluate this at 2, 0, because that's the point that we're analyzing here. So that gradient vector is 1, 2. Okay, and then we're going to calculate the directional derivative. So we have directional derivative at 2, 0 equal to the gradient vector, which is 1, 2, dotted with the unit vector for which we're looking at the direction. And so what we get here is, let's see, this would be 2/5 multiplied by -3/2 plus 2 times 2, so 4. And we happen to get, if we take 4 as 8 over 2, we happen to get 2/5 times 5/2. So we actually get a rate of change or a slope of 1 in the direction of Q. Okay, now I had mentioned this already when we were starting to talk about the gradient of the level curves, but the next part of this asks for what is the max rate of change and in which direction. So I had already mentioned that the direction at which we have the max rate of change will be in the direction of the gradient. So that would be 1, 2, which is what we found in the previous part. So that's our direction, and the max rate there, so the steepest positive slope at the point P will be the magnitude of the gradient at that particular point, which is going to be the square root of 5. And that's for part B. Okay, let's move to the next page. All right, we're just going to try a couple examples here where we're trying to maximize something. And again, we're looking for the gradient's help in determining that, because the gradient will dictate where the max rate of change occurs and in which direction. So we have the temperature at a point XYZ in space given by the equation for T. And T is measured in degrees Celsius, X, Y, and Z in meters. In which direction does the temperature increase the fastest at the point 1, 1, -2, and what is the max rate of increase at that point? All right, so we're going to find the gradient vector first. I'm going to go ahead and write the equation for T as 80 times the quantity 1 plus x squared plus 2x y, excuse me, 2y squared plus 3z squared to the negative first, just because it'll be easier to calculate using the power rule than the way it's written right now as a rational function. So I'm gonna write down the gradient, but I'll pause that because it's just a lot of writing, and then I'll come right back. Okay, so there's a bunch of stuff here, and I actually had to zoom out a little bit because I couldn't fit it all. So when we're doing the derivative here, we have the power rule, so we're bringing the power down, and then we have this quantity to the negative second, and then remember we have to have the chain rule. So the derivative of this first one with respect to x would be multiplied by 2x. The next one has a lot of similar characteristics, except with the chain rule we have multiplication by 4y, and then the last one would be multiplication by 6z for the chain rule. Notice that we have a lot of repetition and a lot of parts that we can actually factor out. This may help, I think, in terms of organization. So we could factor out, if you notice, a negative 80 times 2 as part of our greatest common factor. So we have a negative 160. And then we could factor a 1 plus x squared plus 2y squared plus 3z squared to the negative second out as well. So this is going to be our greatest common factor. We're going to scale the vector. And when we do that, we actually get a really simple vector in return. And, again, like let's say that it was asking for the particular direction for which the function has the greatest rate of increase. You could actually take away the scale and just look at x, 2y, and 3z because it's a direction. Now, again, when we're being asked in this problem to also come up with the max rate of change, we obviously need to keep everything as is. We can't just cancel certain things. We can't cancel the scale factor to this. But I think that it might just help us to simplify the whole vector initially by taking that greatest common factor out. Okay, let's go ahead and take a look at this gradient in terms of the points. So 1, 1, -2. And that gives us negative 160. And if we plug in 1 for x, 1 for y, and -2 for z into this large quantity, we end up getting 16 to the negative second. And then in our vector, that's a much easier calculation. We get 1 and then 2 and then -6. And we could write this, without a calculator, we could maybe write negative 160 as negative 10 times, let's see, it will help us to do negative 10 times 16, because then we can think of 16 to the negative second as 16 times 16. So I'm just trying to brainstorm ways to simplify this. That way, when I cancel, I get negative 5/8 multiplied by 1, 2, and -6. So I think that's about as simplified as we can get that gradient vector. Now we're going to initially put our answer down for our direction, and that's going to be just this gradient vector. So the direction in which the temperature is increasing the fastest will be negative 5/8, 1, 2, negative 6. That's our direction. And then to answer the question is, what is the max rate of increase? That is the magnitude of this vector. And so when we take this magnitude, remember this this scale factor of negative 5/8 is helpful just because we don't have to worry about that. We're taking that squared and the square root. So we end up getting just 5/8 out of that. And then we have the square root of 1 plus 4 plus 36. So that's going to give us 5/8 multiplied by the square root of 41. So again, algebraically, I think it's easier to have those factors taken out, especially if we don't have a calculator to work with on it. All right, let's try example 8. So example 8, we have just a generic function f of x, y, z, and we're looking at a point 3, 6, negative 2. We want to do the same thing, find the max rate of change and in which direction. So, again, it's nothing really new here, just a different problem or a different function. So if you want to try it on your own and then pause the video and come back and check your work, you certainly can. I'm going to just pause it and write out the gradient. Okay, so here's our gradient, and again, it's kind of a lengthy one. Keep in mind that we're doing the power rule again, so bringing the 1/2 power down, decreasing the power by 1, and then the chain rule is applied to each of these terms. Now, if you notice, every one of these terms has a 1/2 and a 2, and so those would obviously cancel. And then there's also this greatest factor that we can just take out, similar to that last problem. So we can take the x squared plus y squared plus z squared to the negative 1/2, factor that out, and then what we're left with is simply x, y, and z, which is sort of helpful there just to simplify. All right, let's take a look at the gradient at our point. So we have the gradient of f at 3, 6, negative 2. Okay, in our factor there, we have x squared plus y squared plus z squared. So that gives us 9 plus 36 plus 4, which is going to be 49 to the negative 1/2. And then, of course, the vector is exactly the same as the point because each of the values connect to x, y, and z. So this gives us 1/7 and then 3, 6, negative 2. And that's going to be our direction. Okay, now in terms of the max rate, that is the magnitude of this. So again, we take the 1/7 squared and then the square root, so that obviously gives us 1/7. And then we have the square root of 3 squared plus 6 squared plus negative 2 squared, which we basically already did. So we end up getting 1/7 multiplied by 7, which is, of course, 1. So we actually have a nice simplified maximum rate, similar to one of the other problems we did. All right, let's move on to our last example in this video. So we're going to do example 9, and then the last video of this particular section, we'll just talk about the connection to tangent planes. So again, this example is not necessarily anything new to what we've been talking about, just a different function. So feel free to try it on your own. You could pause and check your work. We're looking at this function v, which is the electrical potential over a region, space, based on a point x, y, and z. So we're going to find the rate of change of the potential at the point 3, 4, 5 in a direction of v. So our first step, obviously, is to calculate the magnitude of v so we can set up a unit vector. And v is 1, 1, negative 1, so our magnitude is the square root of 3. So our unit vector is 1 over root 3 of 1, 1, negative 1. All right, then let's go ahead and calculate the gradient of v, capital V. So our gradient is going to be 10x minus 3y plus yx, and then negative 3x plus xz, and then our last component will be xy. And then, of course, we're going to take this gradient and analyze it at the point 3, 4, and then 5. So in this first one, we get 30 minus 12 plus 20, which is going to give us 38. and then we get negative 9 plus 15. That's going to give us 6, and then x times y will give us 12. So there's our gradient vector, and then we want to calculate the rate of change, so we're going to do the directional derivative based on all the information we got, which is going to be the vector 38, 6, and then 12, dotted with 1 over root 3 times 1, 1, negative 2. Excuse me, 1, 1, negative 1. And that will give us 1 over root 3 multiplied by 38 plus 6 minus 12. And that gives us a rate of change of 32 over square root 3. So there's our answer for part A. All right, for part B, we're going to look at in which direction does V change most rapidly at the point P. And of course, we know the answer to this will be the gradient vector at that point, which is going to be 38, 6, and 12. And then for part C, it asks us for the max rate of change at P, which again we know is the magnitude of the gradient. I'm not able to do that one by hand, I don't think very well, so we'll use a calculator to simplify this one. I'll pause and do that. Okay, so what I get for that is 2 multiplied the square root of 406, which I think is about as simplified as we can get. Anyway, okay, there's example 9. So the last video in this section will just talk about tangent planes and the connection to the gradient. Thank you.